If all lithium atoms are lithium, why does some weigh more than others? In this lesson, you'll learn what isotopes are, why they share the same chemical properties, and how to calculate relative atomic and formula masses. Remember, you can grab the guided notes below if you'd like. Let's get started. Isotopes are atoms of the same element, with the same number of protons but a different number of neutrons. This is a key definition that you need to learn. Once again, I would strongly suggest creating a flashcard with this on to help you memorize it. Let's take a look at these two atoms of lithium. Using our knowledge on nuclear symbols from the last lesson, we can see that they both have the same number of protons, which they have to, as they are both atoms of lithium. They also have the same number of electrons, but crucially, although they are both atoms of lithium, they have different numbers of neutrons. Therefore, they are both isotopes of lithium. Some elements, like hydrogen, only have a few isotopes, whilst others, like xenon and cesium, have lots. In fact, both xenon and cesium have 36 known isotopes, the most out of all of the elements on the periodic table. Now, the tricky thing about isotopes is that they all react in the exact same way. I could take any one of the 36 isotopes of cesium, and chemically, they would all be identical. Let's take a closer look at these two lithium atoms to understand why. We can see from the diagrams that although the nuclei of these two atoms are different, lithium-7 has one more neutron than lithium-6, the number of electrons, and therefore the electron configuration, is identical. It is the number and arrangement of the electrons that determines the chemical properties of an element. The reason why lithium is less reactive than potassium is because its outermost electron is closer to the nucleus, so the forces of attraction holding it in place are greater. The reason why both potassium and lithium are very reactive metals is because they have just one electron in the outermost shell. Since isotopes will always have the same number and arrangement of electrons, they will have the exact same chemical properties. Although isotopes have the same chemical properties, their physical properties can differ slightly, most notably their mass. And that difference matters, because when we compare the masses of different elements, not all atoms of an element weigh exactly the same. That's where the relative atomic mass comes in. The relative atomic mass of an element, often written as AR, is defined as the average mass of an atom of an element compared to 1/12 the mass of a carbon-12 atom. In other words, it tells us how heavy an atom is on average, taking into account all the naturally occurring isotopes and how common each one is, something we call its relative abundance. The relative atomic mass for any element is given to you on the periodic table, but unfortunately students often confuse this and the mass number up. Remember that mass numbers are part of a nuclear symbol and can only ever be whole numbers. They are unique for each isotope of an element and are not found on the periodic table. So if relative atomic mass takes into account all the isotopes of an element, how do we actually calculate it? Well, we use both the mass of each isotope and how common each one is, its relative abundance. The idea is simple. We multiply the mass of each isotope by its own relative abundance and add those values together, and then divide that total by the total abundance. That gives us the weighted average mass of all of the atoms of that element. Now that might sound and look quite complicated, but let's take a look at an example to help make it clearer. We can calculate the relative atomic mass of an element using its isotopic data. Chlorine has two common isotopes, chlorine-35 and chlorine-37. Roughly 75% of chlorine atoms are chlorine-35, and around 25% of chlorine atoms are chlorine-37. So if we wanted to calculate the relative atomic mass for chlorine, we would take the mass of its first isotope, 35, and multiply that by its abundance, 75. Then we add to this the mass of the second isotope, 37, multiplied by its abundance, 25. We then divide this total by the total abundance, which in this case is 100, as 75 plus 25 makes 100. This gives us a relative atomic mass for chlorine of 35.5. Hopefully that now looks less intimidating than it did before, but let's work through another example to make sure we've got it fully sorted. I'd suggest pausing the video here and having a go at calculating the relative atomic mass to yourself first. Give your answer to 1 decimal place. So same process as before. We multiply the mass of each isotope by its relative abundance and add those values together. We then divide that total by the total abundance. You should have got a total of 3,615 for the masses multiplied by their abundances, and then a total abundance of 43. Dividing 3,615 by 43 gives us 84.1 to 1 decimal place. Well done if you got that correct. If you haven't got the correct answer, look back over your work and compare it to the answers on screen to find out where you went wrong. Now, you might have also been tempted to check your answer with the relative atomic mass for krypton given on the periodic table. And if you did, you may have thought you got the incorrect answer, because on the periodic table, krypton has a relative atomic mass of 83.8, not 84.1. But this brings us on to a question that sometimes pops up in an exam, and that is to explain what might cause the relative atomic mass of a sample to be different from the relative atomic mass given on the periodic table. And that's because the sample you use might contain different isotopes, or the same isotopes but in slightly different abundances compared to the natural sample the periodic table value is based on. So now that we've seen how relative atomic mass takes isotopes into account, let's move on to how we use those values. Every substance, whether it's a simple molecule or a giant ionic lattice, is made up of atoms. And since each atom has its own relative atomic mass, we can work out the total mass of a whole molecule or formula unit by simply adding them together. The relative molecular mass, often written as MR, is the sum of all the relative atomic masses of the atoms in a molecule. For example, in a molecule of water, H2O, there are 2 hydrogens and 1 oxygen. Each hydrogen has a relative atomic mass of 1, and oxygen is 16. So the relative molecular mass of water is 2 times 1 plus 16, which gives us 18. For compounds that aren't made of molecules, like ionic compounds, we use the term relative formula mass instead. It's the exact same idea, you just add up all the relative atomic masses shown in the formula unit. So for sodium chloride, we have 1 sodium and 1 chlorine represented. Sodium has a relative atomic mass of 23, and chlorine 35.5, giving a relative formula mass of 58.5. And that's really all there is to it. Relative molecular and formula masses are just the total of the atomic masses in the chemical formula. Now, you'll use these values a lot when we start looking at moles and chemical equations later on. But for now, well done. You've mastered isotopes, relative atomic mass, and relative formula and molecular masses. You've seen not just the definitions, but also how to calculate these values step by step. To really lock it in, check out the revised video on this topic. It's designed to help you recall all the key points quickly and confidently, so you're ready for that exam practice. Don't forget to subscribe if you haven't already, and I'll see you in the next video.